Welcome to the National Space Society's Space Settlement Contest Grand Prize winning presentation. My name is Lynn Zielinski. I sit on the Board of Directors for the National Space Society and am Vice President of Education and Outreach. For more than 25 years, students ages 12 to 18 have participated either as individuals or as teams in the contest from anywhere in the world. In 2020, more than 14,000 students submitted their entries to the competition, and it was about 26,000 entries that have come in from 22 countries, and that's absolutely amazing and very competitive. And it's amazing that all of these students are so innovative, creative, and have a sense of passion to them for designing these space settlements. It's very exciting. The grand prize winner receives a $5,000 scholarship from the Herman Rubin Endowment and a star map crystal. The crystal shown here is a 3D map of the stars located within 5 parsecs of our sun and solar system. And these stars are important because in the past decade, thousands of exoplanets have been discovered within our galaxy, and some of these stars may have exoplanets that could be habitable for life. And that exemplifies the mission of the National Space Society, which is to settle these worlds and have people living and working in space to develop the benefits of space towards humanity. So with that, I'd like to introduce from El Toro High School in Lake Forest, California, sponsored by his teacher, Trevor Strickland, the grand prize winner for the 2020 Space Settlement Contest, Sean Kinney.
Hello, my name is Sean Kinney, and I am a 12th grade student from El Toro High School in Lake Forest, California. My submission to the National Space Society's Space Settlement Contest, titled Stern Habitat Colonization of the Kuiper Belt with Current Technology, won the grand prize for 2020. It is named after Alan Stern, the lead investigator for NASA's New Horizons mission. As you might guess from the title, the paper details a settlement orbiting a small Kuiper Belt object, 486958 Arakoth. The location was chosen because Arakoth had just been visited by the New Horizons probe in 2019, and I thought the challenges of designing a space settlement in this region would be interesting. The Kuiper Belt is a region of space outside the orbit of Neptune, somewhat similar to the asteroid belt, but dozens of times more massive and much colder, causing bodies there to contain large amounts of ice and organic material, as well as rock. One question you might be asking is why anyone would want to place a space settlement in the Kuiper Belt. As the Kuiper Belt is so far from the sun, sunlight is over 1,000 times weaker there than at Earth's orbit, making lighting and power generation very difficult, as the only way to light and power the settlement is by concentrating sunlight with massive arrays of mirrors. So, is there any reason at all to have a space settlement here, given the disadvantages? Firstly, the Kuiper Belt is very large, containing over 50 times the mass of the asteroid belt. This alone would seem to ensure that it would eventually be exploited. More importantly, these bodies are rich in resources not found elsewhere in the solar system in large quantities. The most valuable of these is likely to be nitrogen. Nitrogen is not very common on small bodies in the solar system, and the only practical sources of it in large quantities are the Earth and Venus, large icy moons such as Titan and Ganymede, and Kuiper Belt objects and comets. Nitrogen makes up 78% of the Earth's atmosphere, is a component of all proteins and is therefore needed for life, and is also necessary to make nearly all explosives, many rocket fuels, and very strong polymers such as Kevlar. All of these will create a very large demand for nitrogen. Fortunately, as you can see from the chart, nitrogen is fairly abundant, making up about 1% of the material by mass. While this might not seem like a lot of nitrogen, it is far more abundant here than on the moon or asteroids. In addition, there is no shortage of other materials necessary for life. You might be wondering how one could practically construct a settlement housing hundreds of thousands of people in space for permanently. As zero gravity has many well-documented health effects, it might seem impossible to have permanent habitation off of a planet. However, a solution to this has been known for quite some time. If you make the settlement a rotating cylinder, sphere, or torus, and have ground on the inside, centripetal force will simulate gravity, will mimic gravity. The image on the left shows a view of a toroidal settlement, while the image on the right shows a view of a cylindrical one. If you notice, in these examples, the rotating sections are exposed directly to space, and most or all of the structure rotates with it. However, my settlement looks different from these designs. Here is an animation zooming out from a tower to eventually show the whole settlement. The overall structure is a disk with several concave depressions due to the need to concentrate light. In the middle of the depressions are towers, which we will talk more about in a bit. You saw two other concepts of space settlements on the previous slide, where the rotating cylinder or torus was exposed to space. However, in this design, the cylinders are inside a non-rotating tower in order to connect them to the rest of the structure, including the mirror arrays for concentrating light. Unlike most other designs, in my design, there are multiple rotating cylinders where people live and work inside the towers in the middle of the depressions. The overall structure does not rotate, but instead each individual rotating cylinder spins inside it, as you can see in the animation on the right. Which is a cutaway view of one of the towers showing a rotating cylinder inside a non-rotating tower. The settlement as a whole does not rotate as it orbits around Arrokoth, and the front side always faces the sun. The depressions on the front side are arrays of mirrors that concentrate light onto the towers. The flat-looking areas are actually made up of a huge number of much smaller arrays that concentrate light onto solar thermal generators for electricity production. This works by having concentrated light heat up a fluid such as steam, which then passes through a turbine, generating electricity in the same way as coal-fired or nuclear power plants. This allows for higher efficiencies than photovoltaic cells, as long as it points directly at the sun. The top part of this image is a front view of the settlement, and the bottom part is a cross-section from the side. Again, while the entire structure does not rotate, the cylinders inside of it do. In this way, it is very similar to other space settlement designs, even though it might look almost nothing like them at first. This shows how the circular areas on the front view are the depressions as you saw earlier. The image on the left is of a concentrated solar installation in Nevada that works on the same principles as the mirror arrays in the settlement. The image on the left is a cross-section of a non-rotating tower. The image in the middle is another cross-section of the tower, but zoomed in on just one cylinder in its immediate surroundings. The purple dashed line is the axis of rotation of the cylinder. You can also see the windows that let light in that is concentrated by the mirror arrays into the cylinder. The image on the right is a rendering showing the cylinder inside one of the towers. The image in the middle is a cross-section of one of the cylinders viewed from the side. If you see the yellow square that expands outward to the top left to show the individual floors and mirrors in more detail. The animation on the lower left shows a cylinder spinning inside one of the towers viewed from the top, while the animation on the right shows a cut through of the cylinder and tower and one of the cylinders and towers viewed from the side. Another big difference between this and other space settlement designs is that there are multiple levels inside each cylinder. The green areas in the rightmost inset are floors, with the outermost one being the ground level where most housing is located, and levels closer to the center being used for purposes such as agriculture. The blue areas are spaces where light is bounced through. If you see where this blue area extends to the outer edge of the cylinder, this is where the windows on the cylinder in the image in the middle are located. Light from the sun, concentrated by the mirror arrays, is bounced through the windows and into the cylinder where it is distributed to light all the floors. Here is an animation showing how light travels inside the tower in cylinders to light all the floors. First, light comes in from the parabolic mirrors, then is reflected by more mirrors inside the cylinders to light all the levels. Moving the mirrors can light different halves of the cylinder to simulate day-night cycles. Here are some drawings that show how light is concentrated and then distributed inside the cylinders in more detail. The section of this image on the left is a very zoomed-in view of the inside of one of the cylinders, while the part on the right is much more zoomed out and shows the mirror arrays and towers in their entirety. The mirror arrays concentrate light and then reflect it through the windows in the sides of the towers and cylinders to then light the inside of the cylinders. Let's go back to that picture showing the cylinder and its a cylinder and its immediate surroundings that you can see on the left. I mean the right. I'm sorry. There are two types of rotating cylinders in this settlement. The first are habitation cylinders, located in the large central depression as they need more light. This is where people live and also where food is produced. The second type are industrial cylinders, located in the towers in the smaller depressions, where industry that would not benefit from zero-G conditions is located. However, these rotate slower than the habitation cylinders to simulate a gravity a tenth as strong as Earth's at their edge to make it easier to move objects and materials. Some plants are grown in the industrial cylinders for pykrete, a composite consisting of plant fibers and water ice that is used as a structural material in unheated parts of the settlement. But electricity is generated outside the cylinders on the flat areas by solar thermal generators because they're much more efficient than solar panels. The sections of the tower near the cylinders contain areas for zero-G industry and pressurized dry docks for the assembly of large objects in zero-G. Material is moved from the surface of Arakoth to the settlement in order to process it. Small Kuiper Belt objects never reached high enough temperatures in their formation to cause their ices to melt, and are therefore pretty much homogeneous and very porous. This means that automatically removing material from their surfaces should be relatively easy, with these materials then being transported to the settlement for processing in the industrial cylinders. This involves many steps to separate all useful substances from each other and would take too long to fully explain in the time I have been allotted. If you're curious, just read the paper that has been uploaded to the National Space Society Space Settlement website. However, the flowchart on the screen right now shows some of the initial processing steps. All of the technologies used are fairly well established today. The main material being produced for export is nitrogen, but almost everything is useful in one way or another. Due to the large amounts of volatiles available to the settlement, there is a wider choice of possible structural materials than with settlements located in the inner solar system. Since tensile strength is what holds the cylinders together, instead of compressive strength being needed to resist weight, as with most buildings on Earth, Very strong, light polymers, such as Xylon, whose molecular structure is shown on the left, can be used. This allows for rotating cylinders to either be built much larger or use a much smaller amount of structural materials. Since materials like Xylon and Kevlar contain large amounts of nitrogen, it is likely they will make up a large part of the demand for nitrogen being exported to the inner solar system. The photograph on the right shows a pykrete reinforced dome that was built in Finland. Pykrete is another unusual structural material, a composite made up of plant fibers and water ice. While not particularly strong, due to the large amounts of ice in Kuiper Belt object material, it can be used in portions of the settlement where not very much strength is needed and temperatures are well below freezing, like supports for the mirror arrays. The large distance between the settlement and the inner solar system means that the transportation of people and materials will take quite a long time. If only chemical rockets were used, only low energy trajectories, such as the one shown here, taking decades each way would be practical. For example, the New Horizons probe was launched in 2006, but only flew by Arrokoth in 2019. Fortunately, electric propulsion options, such as electrostatic ion thrusters and VASMIR, which stands for Variable Specific Impulse Magnetoplasma Rocket, exist today and allow for much higher speeds. One-way travel to or from the settlement to the inner solar system should take between 1 and 5 years, depending on what fuel is used, the percentage of the ship's starting mass that is fuel, and available power for the engines. This is much quicker than it took the New Horizons probe to travel to Arrokoth, which is 13 years. A faster trajectory would look something like the straight yellow line. In most cases, VASMIR would likely be used, as it lacks a grid or other components that are in direct contact with the exhaust. This means that erosion of the grid or other components due to chemically reactive species in the exhaust is no longer a concern, massively widening the possible choices of fuel. Electricity for powering the engines can be generated either by solar power with large light mirrors concentrating light far from the sun, or with a nuclear reactor. While 1 year is much shorter than 13, it is still long enough that passengers on a ship in 0G would suffer serious health effects. Therefore, ships carrying people would have to have rotating passenger sections in order to simulate gravity. Below about 200 meters in radius, a rotating habitat with a simulated gravity, the same as Earth's at the edge, would need to rotate fast enough that some people would get nauseous. So the radius cannot be smaller than this. However, the size and mass of this section can be decreased by making it a torus instead of a cylinder, and even more by only having portions of a cylinder connected by a central bar instead of an entire torus, as you can see in the animation here, which is a rendering showing what one of these passenger ships might look like. There is so much more to this project than I have been able to show you in the time I have been allotted. However, you could see that even with only currently existing technologies, it would be possible to build a self-sufficient space settlement even as far from the Earth and Sun as in the Kuiper Belt. I would like to thank my parents, my physics teacher, Trevor Strickland, the National Space Society Vice President for Education, Lynn Zielinski, for helping me put this presentation together, and Al Globus and the National Space Society as a whole for making it possible for me to give this presentation. If you would like to see my paper, a link just came up now. I thank all of you for your time.
At this point, I'd like to have a little conversation with Alan Stern and Sean Kinney. I'd like to introduce Dr. Alan Stern. He is a planetary scientist, a former NASA Science Mission Directorate Associate Administrator. He's a former board chair of the Commercial Space Flight Federation, and he's a current member of the National Science Board of the National Science Board. Okay. So in 2020, this is really amazing. Dr. Stern, was selected to fly as one of the first research scientists for a NASA-funded program from Virgin Galactic. So he will be flying, I believe, in the next year or two. This is really exciting news. So congratulations, Alan, on that. That's really great. Alan has also been on 29 NASA and ESA space science missions, I believe 14 of which he was PI, the professional, a principal investigator. And including the nearly $1 billion mission for the NASA New Horizons program, which flew a mission to both the Kuiper Belt and Pluto. It's a wonderful, extraordinary mission. And he's also coordinated many other programs. He is a fellow of the American Association of Science, the Royal Astronomical Society, and the Explorers Club. In 2007 and 2016, he was named the Times 100. So welcome, Alan Stern, to this conversation between you and Sean Kinney.
Thank you. Thank you, Lynn. Why don't we begin? And let me start, Sean, by saying congratulations.
Thank you.
I read your report and I saw your presentation. And it's not only creative, but it's thorough. And you should be very proud of yourself to get this recognition from the National Space Society.
Thank you. I'm very honored.
So what I'd like to do is just kind of have a conversation and ask a few questions. But I wanted to say how honored I am that that you named the station in my honor. I never thought in my life anyone would ever name any spacecraft of any kind, much less one so grandiose as your station, for me. And thank you. It's flattering and it's an honor. But I also want to say I'm wearing a New Horizons mission shirt because New Horizons is really a big team of people that made the exploration of Arrokoth possible. All of space flight is a team sport. And so in honor of my team, I'm going to be sending you, Sean, this shirt, not the one I'm wearing, but one that is your size and which fits you, as a further recognition of the honor of this award in honor of your work. But let's jump. You're very welcome. And let's jump right in. How did you get the idea for doing a station not only in the Kuiper Belt but orbiting Arrokoth?
Well, I was obviously I was following quite closely the New Horizons mission, and I was also thinking about for this contest how I could differentiate my station from other ones. And I thought, what's one of the worst possible places in terms of available resources, available energy, etc., that I could put a space settlement where it still might be viable? And I thought that the Kuiper Belt, being so far from the sun and Earth, would be a good choice for this. And also, Arrokoth had just been visited by the New Horizons spacecraft. It was a small Kuiper Belt object and the only one that has been visited by any spacecraft or observed in detail. So I thought that would be a good location for it, and because of the challenges it would and opportunities that it would create.
Okay, well, let's talk about the solar concentrators a little bit. How did you get the idea for them as opposed to just using very much larger solar arrays to power the station?
All of the math and stuff I did myself. I didn't I'm not aware of any really detailed stuff for space settlements that has involved solar concentrators like that. However, the idea, I did see it before, even if it wasn't in too much detail. I think both on one of O'Neill's original papers back in the 70s, and also from the YouTube channel Isaac Arthur, which I believe has also been awarded an award by the National Space Society for 2020.
That's really cool. I didn't know that about the O'Neill stations doing that. But let me ask you about the gravity level inside the cylinders. Is it going to be a full 1G?
In the habitation cylinders where people are located, it is 1G at the outermost level where most people live. Closer to the center, it will obviously be a bit lower in that. So agriculture is mostly located there, so you don't have people living there full time. That would hurt. That could cause negative health effects. In the industrial cylinder, in the industrial cylinders, it does rotate still, but it's slower. So the gravity at their outermost level is only 1/10 of the gravity at Earth. This is so it's easier for structural stresses for the cylinder as a whole, and also for any industrial equipment inside, and also just to make it easier to move around large amounts of materials. I came up with that idea myself. I haven't really found it anywhere before. It just seemed like something that might be a good idea to me, and it may not under more professional investigation.
So when you were putting this all together, when you were doing the design and the creative part of the work, what was the hardest part?
The hardest part was probably coming up with the processes for processing the material, because there were a bunch of different papers that I had to sort of all piece together to get a complete list of stuff and in what concentrations it was present. Mm-hmm. Also, what was a lot of work was making the 3D renderings and animations that you saw in the slide presentation. Those weren't in the original paper because I didn't have time before it was due, but I think it really was useful for the presentation as a quick way of explaining what everything looked like and how it came together.
And what was your favorite part of the whole project?
I really liked most of the stuff in the project. I enjoyed the work and coming up with different ideas of how to solve all the different problems. And I obviously really liked winning it, and I liked pretty much everything.
Well, that's great. So, what role did your physics teacher play in coming up with this idea and then actually executing it?
I did most of the creative stuff and writing myself. However, he was very useful in that he looked over the paper and helped me proofread it before I submitted it and caught any flaws that were in there.
That's really great. He could do that. Mm-hmm. So we're running out of time, but we still have a couple of minutes left. What's next for this concept? Do you have any further plans to develop it or publish the description?
Not at this time. I may try to get it published in an edited form at a later date. I am actually working on a different paper for space solar power that might be published in the Space Settlement Journal from the NSS later this year. But yeah.
This is a tremendous amount for anyone to accomplish in high school. I am so impressed. And I did a lot of science fair projects, but nothing of this scope. So I am really impressed. Tell us and tell the listeners, the audience, what's next for you after high school? What are you planning on doing next?
I applied to a few different colleges, mostly UCs and Cal States, as well as one or two out-of-state schools. Depending on which ones I get into and how much it would cost, I may go to those straight away, or I may go to a community college first for 2 years, so I'm in less debt after I graduate. I'd like to study chemistry in college, and ideally do some graduate school stuff as well, because yeah.
Do you see yourself more in the vein of becoming a scientist, or more like an engineer?
I'm not really sure as of yet. Both seem very interesting.
Well, I want to say congratulations again, and thank you for such a great presentation. both
Thank
the
you.
written and
Thank
the one that you just gave for the NSS.
Yeah.
Congratulations.
Yeah, thank you so much.
Okay, Lynn, back to you.
Thank you, Alan. Thank you, Sean. This has been a wonderful conversation, and the National Space Society is so proud of Sean and the work that he's done. And really, Alan, thank you so much for taking the time to come and speak with Sean. And congratulations on your accomplishments as well. So with that, thanks everybody, and good night.
Thanks.
Thank you.